Lasha and I are going to tag team this presentation. I'm going to start it off by sort of giving a little bit of overview and background for those of you who maybe aren't super familiar with the work we've been doing on our Giant Sequoia AI project. But this is mainly to sort of demonstrate our progress thus far and all we've been able to accomplish this year. To start, giant sequoias are the world's largest trees by volume. They're beloved by the public. People travel from all over the world to see them. If you've ever been able to see them, they're pretty mind-blowing. They can also live for thousands of years. So they're really resilient organisms. They haven't really been recognized to have a lot of natural predators or threats. But recently, because of climate stress, intensified heat, drought, fire events, scientists have observed them to be infested by native bark beetles. So these insects that have coexisted with them on the landscape, are now killing them in as little as 18 months. And until today, detection of these events has really been ad hoc. So essentially just park managers or park employees kind of wandering around the forest and happening upon a dead or dying tree, looking up into the canopy from the ground and noticing these changes. So this sort of ad hoc detection and monitoring is not scalable or feasible for a lot of reasons. Firstly, because the natural range of giant sequoias is sort of this 260 miles long by 15 miles wide band on the western slopes of the Sierra Nevadas. It spans 7 different counties in California, on National Park Service, U.S. Forest Service, Bureau of Land Management, California State Parks, and also tribal lands. So there's a lot of area we're working with here. And then also the real kicker of this is that beetle-infested sequoias die from the top down. So this really subtle crown discoloration, crown browning, is sort of the first signs of attack. So back in December of last year, the WildMe team sat down with National Park Service and USGS employees. This is actually where I met Jason and Lasha. And we kind of set out to discuss how we can reframe our approach and move from this sort of ad hoc ground survey-based detection and monitoring to a more comprehensive and sustainable and scalable approach to detect and respond to this new threat. So our solution was to develop AI tools to automate forest survey and monitoring using satellite imagery. This allows us to bring individual tree monitoring to the landscape level, so that land managers can respond earlier, more quickly, and in more coordinated efforts across all of these jurisdictions that steward giant sequoia lands. To do this, firstly, we are counting and inventorying all giant sequoias. So we really actually don't know right now how many giant sequoias there are in the world. There are estimates. Giant sequoia groves are estimated to occupy around 35,000 acres in California. There's around 75,000, there's around 75 current recognized groves. But using our models, so these are actually bounding boxes from our recent model results. I didn't draw these, the model did this. We're able to count all giant sequoias and really get a sense of where they are and how many there actually are. Secondly, we are counting and inventorying all dead and dying trees. So this doesn't just have applications for giant sequoia monitoring specifically, but also for broader research into fire risks, fire effects, and fuels research, as well as other landscape ecology and forest monitoring research. And then thirdly, the tallest task of our project, I would say, is to create an ongoing health status monitoring system that flags potential beetle-threatened trees at the earliest stages possible. So really at the most subtle crown discolorations that we can detect. This is to be deployed on a monthly basis, on an ongoing basis, and we're also packaging all of our model capabilities into a QGIS plugin. QGIS is an open source mapping and geospatial analysis software. So all of these tools are free to use for partners on this project. I also want to shout out Yijin for her help with the QGIS plugin here. This is an example of one of our model predicted and classified top-down threat trees. You can see this little crown browning at the top of the tree. Okay, so to do all of these things, there's a lot of moving parts. There's a lot of data that we need. Firstly, we need to really strategically acquire historical imagery and also request future imagery to maximize the volume of really rare and important classes to our data sets. So right now we're working with upwards of 40,000 hand labels with 15 distinct classes. And we're not only distinguishing between giant sequoias and other confuser species in their natural range, but also between beetle-threatened sequoias and sequoias with the different types of damage. So here in the red, you can see some fire-damaged sequoias, and then here you can see this really sort of like an early detection of a top-down threat or beetle-threatened sequoia here. And in these images, you can see sort of this time series comparison between some June 2022 imagery and August 2025 imagery, whereas these individuals are healthy, both healthy here. And then in this picture, you can see there's crown browning in this mature sequoia, whereas this one has remained healthy. We are also labeling and training our model to be able to work on as diverse conditions as possible. So this has to do with factors like seasonality, sun angle, sensor geometry, capture settings, but also for structure, topography, fire histories in the landscape. And these images are from so these are not RGB regular images. These are near infrared, red edge, and deep blue bands. But you can see even in the same grove locations or in similar seasons, imagery and trees within the images can look really different. So it's really important for us to be able to reliably predict and classify individuals in as varied contexts as possible. And then lastly, we are prioritizing study areas with proposed ecological risk factors for beetle attack. Namely, these are recent instances of low and moderate severity fires. And then also alignment with known occurrences of beetle attacks. So we have a data set of around 200 known beetle infested trees, which is very, very small compared to how many sequoias there are. And we're also wanting to make our labeling and our training as efficient as possible. So this means targeting areas with the high density of mature sequoias and also named sequoias. So trees like the Sherman tree or the Grant tree that are of really high cultural importance to the parks and to the public at large. Before I hand this over to Lasha for his more machine learning side of things, I wanted to quickly brag on some of our recent model results. So this is a capture from the Giant Forest Grove, which sits in Sequoia and Kings Canyon National Parks. And here you can see the model produced bounding boxes. These three individuals were classified as potential top-down threats. You can see here that they have this sort of subtle crown discoloration. You can really kind of parse it out by comparing it with some other imagery from a few years ago. And then what I was really proud of with this one is that the model did a great job of not giving us a false positive detection and actually labeling this damaged giant sequoia as healthy. We have recently begun doing a lot of validation and sort of feedback loops with park employees to parse out these more subtle false positives. And this giant sequoia does have sort of some crown damage here. Sometimes there's breakage and exposed trunks that can often appear as potential top-down threats. But in actuality, these sequoias are healthy. So the model did label this as a healthy individual. So very proud of that. I'm going to pass it off to Lasha now.
Yeah. It's been an amazing effort, and fast forward to just last week, some pieces came together. We already had the models trained on significant enough data and the platform to run it, for which I'll talk about more. But basically, what I ended up staring at last week was this on my screen. And this is each of the box is a tree, and the color signifies something important about it, which is if it's purple, it's probably a mature sequoia, and if it's red, there's possibly a top-down thread growing in the tree. So on the next slide, so substitute the actual satellite layer, you can actually see the whole forest kind of imaged and the underlying structure appearing with the denser and less dense parts of mature sequoia grows, the disease, and also in the light pink, the dead trees, which can usually be seen as a source of fuel for the future fire. We can kind of see the density of where the fuel's accumulating and where it might be creating potential future hotspots. This is really valuable to see because on the next slide, you'll see a comparison. On the right side, the right square on the big area, that's image right up next to the arrow, is around 200 by 200 meters of land that would take a human expert a couple of days to scrupulously go through and level each and every one of the trees. And this is something that we started off as reference, and we can kind of use this model to expand in areas that basically leave the scale that the humans can do, even from the satellite point of view in the sand. And the process, an important feedback process that we've been using here is kind of using those maps to guide our own labeling effort. So once we start doing some of the areas and keep finding out what some of the interesting classes look like, we can use these predictions to guide us into more of the hotspots or more of the kind of unique places where we can mine for some of the rare classes. To give an idea on how we've been doing data labeling on the next slide, it's just numbers on how we've been growing our data set. And you can see it's a long tail. Some of the classes are pretty rare as defined damage and top-down threat compared to just all the trees we find. So the way we've been shifting is as we scale our data set, and on the left, you can see we kind of tripled it from the initial version, which was early in the winter this year, is to guide us more to the rare classes. And for an average, if our data set tripled, our mature sequoia amounts increased sixfold. Our dead tree inventory increased 15 times because we could pretty early on try to detect dead trees and find vast areas of previous prescribed burns and fires that left a significant imprint. To give you a perspective on the next slide, is just how much we're working with right now versus how much we started with. All the way to the end, to the right, is a small red bar, which is just how much we labeled. And this took months of focused effort and cross-checking with different sources and information. And from that, we could go on to image a big chunk of the park, which would cover most of the known grow boundaries, and image upwards of around 3 million almost trees in the Seki area. Onto the next slide, it's just a couple of examples of what the classes themselves that we're looking for look like, which is this general tree, a dead tree in the bottom left corner, which is really stark. It's just pale white, so it's really easy to find. And something more subtle, like in the orange ring, the top-down thread cases, which could vary from almost half of the tree up top being dead to sometimes so subtle that even we have to kind of ask ourselves whether our decision is right and kind of go back and see it at other time points to realize how the damage has been progressing. And because of this kind of variations, there's different performance we expect in most of the classes. On the next slide, you can see that the dead trees are super easy. We can basically claim 98% precision and recall when testing outside of the domain, outside of the satellite captures, and that's how this grows that the model has been trained on. Where something like Sequoia mature or top-down thread, however, in the newer versions, you can see the progression at around 70 to 80%. This is way beyond the expectations of some of the other approaches using machine learning, for example, LiDAR surveys, which kind of are a hit or miss, and not to mention that the scale much higher than satellites. So kind of at this point, this third version that we've been doing for the last couple of months made us say that, okay, our model's kind of giving us numbers that are good enough that we could actually put this out in real life and see if our expectations actually hold up. So that's what we did. And on the next slide, props to Eugene, which really was a really fruitful use of her sprint here, last sprint at WildMe. We put together an initial version of a plugin in QGIS, which is a standard software that everybody operates. We put our models there, and what you could do is image all of the region and kind of zone in. That's the biggest difference from the previous approaches where we would be statistically accurate because they were calibrated on terrains. So when you were to zoom in onto those individual top-down threads, it would not reflect whatever was happening on the ground. Some pop on the LiDAR of a dead sequoia might have found a rock or might have found a bush that might not necessarily be the same height as the stump, but not the same. So going in up close on the next slide, we can basically zoom in and gather information on the individual tree level. And we can simulate a field trip. If we go out and find a place that's near a road, you can see on the bottom of the picture, there's a highway. We can find a really interesting case in bright purple at the arrow of a dead sequoia. And we can basically put our little Google Street Maps man in there and see if this is actually true. So we go and transport, and what you can see is at the base of the arrow, not the tip, is where we're standing. And you can kind of orient yourself with to the right is a sugar pine, which is not boxed because it's not a sequoia, up to the right there. And two sequoias to the left, two sequoias on the right, and at the tip of the arrow, there's a dead sequoia that we see on the map. And this is, of course, one of the peaked examples we picked, but we keep going in and on. We find these confirmations that what we're saying is actually really big and important processes that are happening on the ground, just registered as a small little box on our QGIS screen. So this is really exciting. And this gives us a motivation to follow up with our next step, which is on the next slide, our collaboration with the partners, NPS, USGS, and possibly maybe Ancient Forest Society and the others, to actually image most of the sequoia growth at the latest capture. We're working with Airbus and Connected Conservation Foundation with a grant on the imagery where we could pick out a 109 square kilometer area containing most of the growth. This could probably be around 40% of the sequoia population in the world, and do a tasked custom capture just for our case, which was collected on the August 27th. And this is helping us build a tree map of all the area to be used as a reference for the field guides. And what the NPS and USGS is doing actively now is they've had their whole department shifting to drone verification. So we have this active feedback loop now that where we can find some of those trees, give it to them, and we have this really active and ongoing communication collaboration where we meet monthly, and they can go and check and confirm some of the cases and return to us some important data, which is some of the confirmed cases and also cases where we were wrong, but because of some deceiving reason that looked like damage. So we're basically strengthening through negatives and the positives through these feedback loops. And we're trying to do this rollout to follow the park and do verifications as we go along and do our next step, which is on the next slide, kind of harnessing and looking into temporal domain, because our maps right now are snapshots. And usually with satellites, you can, over the years, see some progression. It will give you extra info. And sometimes, as on the bottom example, the angle will actually give you a peek on some of the areas that you can't see on one of the angles. So it's really important to harness this to get a more accurate predictions. But there's another really important factor of why more imagery is valuable and more kind of looking into a temporal domain, which is sometimes we are not sure whether we're looking at the top-down damage or not. So once we actually do deploy the model, we are more certain of ones that have progressed more. So right now we're working in the Airbus to get access to historical archival data, whereas we can go back and look back in the data from the trees we found that have progressed and kind of see how the disease actually started and developed, and try to put the same pattern into the model to reflect that, so that we can basically advance our end of how early we can detect something like this. And there's really fascinating signatures in the spectral domain, especially hyperspectral, where we can't perceivably see, but the drought or water stress, spark stress will sometimes manifest as reduced activity on the lower bands of the capture. So we're kind of hoping to, in a way, uh, advance the frontier in terms of what we can actually label as a top-down threat, and actually capture some prior uh, patterns that emerge just before the attack progresses. And the last important step on the next slide is that we've kind of honed down a great pipeline with feedback loops and a process that helps us grow and iterate really fast, and also arrive us at a platform now, because we basically created something that are creating. It's a ways of there, but a wild book for trees. And there's no reason that the one of the species of trees is specifically different from the other. So this has big potential to go beyond sequoias, and all the learnings and infrastructure be cross-applied to trees of heaven, where we have spotted lanternfly problem, emerald ash borer, or coastal redwoods, which also could have similar invasive problems.